Right, so today we will be discussing orbits of permutations, and the alternating group, which is denoted by A sub n, and then the quotient group, right? So let me start by giving you the definition of, or at least let's define the orbit, sorry. So let me first write orbits alternating group an, and then later on we will define the quotient group. Right, so for orbits, let's take a permutation of any given set A, right? So what does it mean? We take elements in this set and we permute them, right? You can arrange them in however order you like. That would be a permutation. So each permutation let's denote this by sigma of a set A determines a partition of A into cells with the property that, I'll write it within quotations. For any two elements that you take from this set A, we say that A is equivalent to B if and only if and only if B can be written as sigma nth power of A for some n an integer, right? So you take the element A, you permute it n times until you get the element B. If that is the case, if you can permute A n times to get B, we say that A is equivalent to B, right? Or in other words, we can say that A and B belong in the same cell of this partition if you can write B as sigma n of A for some integer n, right? With this, let's define an orbit for a given permutation, sigma. Definition, let's take sigma to be a permutation. Let sigma be a permutation of a set A. The equivalence relation, which is given over here, right? So the equivalence classes that are determined by this relation, the equivalence classes in A determined by the equivalence relation given over here. So I'll simply write equivalence relation above are the orbits of sigma. So when you have, if A is equivalent to B, right, that means you can write B as sigma to the nth power of A, right? Sigma A raised to the nth power. Let's put it that way. In that case, A and B will fall in the, or they will belong in the same equivalence class. Those classes would be the cells that we talk about over here, So that would be the partition of A, right? So let's look at one example to understand what it means. Right. Let's take the symmetric group. Let's consider sigma. Let me give sigma in this notation, okay? This is a permutation. Let's take it from S8. Permutation group S8. 1, 2, 3, 4, 5, 6, 7, and 8. Let's send 1 to 3, 8, 6 to 1. And then 5 to. Now, I have not written this in the usual cycle decomposition of sigma in S8. So this is an element in the group S8, right? Now, let's find orbits of this sigma. So we start off with just one element, right? Let's start with the element 1. No, no need to write S8. Let's start with element 1. Then we have, observe that sigma of 1 is equal to 3, right? This simply means through this permutation, we will send 1 to 3, 2 to 8, 3 to 6, and so on. Right, so sigma of 1 is equal to 3. Then let's calculate sigma squared of 1, right? This is equal to, so in this case, sigma of 1 means the power over here is simply 1. Then 1 is equivalent to 3 according to this relation given above here. So 1 and 3 will fall in the, or will be elements in the same orbit, right? Then let's calculate sigma squared of 1. This is simply sigma of sigma 1. This is a permutation. So sigma squared, in this case, we write it as sigma of sigma 1, refers to the composition of these two functions. So we've got sigma of 1 is simply 3. Sigma of 3 is sent to 6. So this is equal to 6. So now we see that 1, 3, even 6, they fall in the, or they belong in the same orbit, right? Even if you look at simply this relation, we see that 3 and 6, they belong in the same orbit. Now, let's calculate sigma cube of 1. This would simply be sigma of sigma squared of 1, right? Sigma squared of 1 is 6, and through sigma, 6 is sent to 1. Right? So we see that 1 is fixed under sigma cube, right? So when you continuing this way, we see that sigma raised to the 4th power, sigma 5th power, they will keep on continuing producing the element 136, 136 in that order, right? So we see that the orbit containing 1 is simply the set 1, 3, 6. Right? So the orbit containing 1 is simply 1, 3, 6. And then the same, for this same, instead of saying 1 over here, we could say the orbit containing 3 is also 1, 3, 6. For any of these elements, this is the orbit containing those, right? Okay, now let's find now. Okay, let's see. We have up to 8 elements, right? We have up to 8 elements, 1, 2, 3, up to 8. We have over here 1, 3, 6. Now, we want to see what the partition is of the set A. A I will write as simply 1, 2, 3, 4, 5, 6, 7, 8. Right now, A is this set, and this is a permutation over elements of this set, and we understand it's an element in the permutation group S8, right? Now we want to see how the partition is over A by sigma. We have 1, 3, 6 in one orbit. We want to find the rest of the orbits by sigma over A. Let's calculate, let's consider an element that is not in this set. So let's go with 2. So I'll write take 2. Let's calculate sigma of 2. Through sigma, 2 will be sent to 8. So this is equal to 8. Now let's calculate sigma squared of 2. This would be sigma of sigma 2. Sigma 2 is 8, right? It's 8. And 8 through sigma is sent back to 2. So sigma squared fixes 2. Right? And if you calculate sigma cube, we come back to 8. Once again, powers of sigma, if you take powers of sigma of 2, we will alternate between the values 2 and 8, 2 and 8. This will equal simply sigma of sigma squared of 2. Sigma squared of 2 is simply 2. 2 will be sent back to 8 through sigma. Right? So the orbit containing 2 or 8, you may say, would be the set containing simply 2 and 8. The orbit containing 2 or 8 is simply the set 2, 8. If you look at A, we have up to 8 elements. We've gotten 2 distinct orbits, right? With respect to 1 and 2 over here. One containing 3 elements, 1, 3, 6. The other containing 2 elements, 2, 8. So let's pick one element in A, which does not appear in either of these sets. Let's go with maybe 4. No, let's go with 4. Let's take 4. We have sigma of 4 equal, if you go to this function over here, 7, right? So sigma of 4 is 7. Sigma squared of 4 would simply be sigma of sigma 4, or in other words, where sigma sends 7 to, right? Sigma of 4 is 7. 7 through sigma is sent to 5. So this is equal to 5. Now let's calculate sigma cube of 4. Okay, this is equal to sigma of sigma squared of 4. Sigma squared of 4 is 5. 5 through this permutation is sent to 4. Right? Once again, you see when you take powers of sigma of the element 4, it goes between the values 7, 5, 4, 7, 5, 4 in that order, right? So the orbit containing the element 4 is the set containing elements 4, 5, and 7. So we can write the orbit containing 4 is simply 4, the set containing these 3 elements. Now you see we have 3 distinct disjoint sets where the union gives you the set A, right? So these are the orbits of sigma. And if you take any element, even 3 from here, and try to find its orbit, you will end up getting these values. Sigma of 3 is simply 6. Sigma squared of 3 is simply 1. Sigma cube of 3 is simply 3. Likewise, you end up getting those the same values, right? Once you have this orbit for one particular element, the rest of the elements that appears in that set will have the same orbit. So you don't have to consider them separately. Right. So the orbits of sigma are given by 1, 3, 6. Then we've got 2, 8, and this last set, 4, 5, 7. Three distinct orbits, three orbits of sigma. The union, this partitions A, right? When you take, these are mutually disjoint. When you take the union, it gives you A. Now observe, let's take, now, but before we actually get to this part, there is a way for us to visualize the structure through these orbits, right? So let me write visualizing the structure of permutation sigma, right? First orbit through sigma, 1 is sent to 3, right? 1 is sent to 3, 3 is sent to 6 through sigma, 6 is sent back to 1. So this is the orbit of sigma containing these three elements. You come to this orbit, going in this direction shows you that sigma of 6 is equal to 1. In other words, sigma will map 6 to 1. Sigma will map 1 to 3, likewise, right? And you go to the second orbit containing these two elements. You have on one end 2, on the other end 8. 2 through sigma will be sent to 8. 8 through sigma will be sent back to 2. Then we have this last orbit containing 4, 5, 7. 4 will be sent to 5 through sigma, 5 to 7, and 7 to 4. So this is one way to visualize the structure of the permutation sigma through these orbits. This is one orbit, this is the other, and the other one. Right? Now, let's go back to the cycle decomposition of sigma, which we have done previously, right? Let's find the cycle decomposition of sigma, right? Let me write sigma first. We've got 3, 8, 6, 7, 4, 1, 5, 2. Right. If we get its cycle decomposition, right, starting with 1. 1 is sent to 3. So we write 1, 3. And go to 3 over here. 3 is sent to 6. We write 6. Go to 6 over here. 6 is sent back to 1. So 6 will be going back to 1. We close this cycle. Then we don't have, let's go to another element that which we don't have. Write 2 over here. 2 is sent to 8. So we write 8. Go back to 8. 8 is sent back to 2. So we close it over here. Now to get the other one, start with 4. 4 sent to 7. 4 is sent to 7. All right. Because 4 is sent to 7, this over here has to be 7 and this over here has to be 5. I have made a small mistake over here because 4 has to be directed towards 7 through sigma. 4 maps to 7, right? Okay, so going back over here, 4 is sent to 7. Go to 7, 7 is sent to 5. Go to 5, 5 is sent back to 4. We close the cycle. This is the cycle decomposition of sigma, right? It's a product of 3 cycles which are disjoint. They have no element in common, right? Now, if you compare this cycle decomposition to these three orbits, right, we see that this first cycle corresponds to the first orbit that you see over here, right? And then we have the second cycle in this product. Now in the cycle decomposition of sigma, what you have here is not the composition of these three cycles. It's simply a product of the cycles. It's not like you're taking two permutations and writing it as a product. What appears over here is simply a product of cycles which defines sigma. It's the cycle decomposition of sigma. This refers to this second orbit, right? And this last cycle refers to this last orbit, right? So what does it mean if you get the cycle decomposition? If you have a cycle decomposition, once you write the cycle decomposition for a given permutation, each of those cycles that are in the product would correspond to an orbit. So in this cycle, you have the elements 1, 3, 6 that will represent one orbit containing the elements 1, 3, 6, right? If you go to the second cycle, it corresponds to the orbit containing the elements 2, 8. So orbit of 2 is 2 and 8. And this last cycle in the product of the cycle decomposition of sigma contains elements in this other orbit of sigma. So we see that once you have the cycle decomposition, you can definitely identify the partition of the set A, right? I will simply refer to it as the set A. And you can simply identify all the corresponding um, orbits of that given permutation. Okay, now I want to make a slight remark over here. Now this is the cycle decomposition of sigma, right? Uh, this sigma I can simply write as 1, 3, 6, 4, 7, 5, and 2, 8, right? Which is the same thing. Now, I can commute these two in the product because this is not function composition. It's simply the cycle decomposition of the same permutation sigma. It's not like you have all these cycles by themselves would represent different permutations. But now in this product, what you have is one permutation. So you can, even if you write the cycle decomposition of sigma in this form, um, it will be correct, right? You can permute these cycles that are in the decomposition um, in this way. But the permutation multiplication, in other words, permutation composition is not commutative, right? Permutation composition is not commutative, but the cycle decomposition, you can write however you like, all these cycles that are in the decomposition of sigma. Now, right, let's take a look at one more example. Let's take identity permutation of S8, right? Then what would be the orbits of this identity permutation? We are permuting elements from 1 to 8. Now we are considering the identity permutation, which is an element in S8, right? That means all the elements will be fixed. 1 will be sent to 1, 2 will be sent to 2. They will be fixed. They will not be sent to a different element. They will simply be sent to themselves, right? Fixed. What is the orbit of 1?
One.
Just 1? Is the singleton set 1? It's a set, right? Orbit of 1 is 1. Orbit of 2?
Singleton set 2.
Yeah, it's the singleton or all these one element sets. So we see that the identity permutation, right? The orbits will be all the singleton sets by elements in A, right? For the identity permutation. So I can write the identity permutation of A uh, leaves every element of A fixed, and the orbits are the singleton subsets or one element subsets of A. All right. Let's do one more. Let's do one more example. Over the same set A, let's take the permutation mu over elements of A. Let's take it to be, let me write first as a function, and then I'll simply write the cycle decomposition. This is 1 over here, and then 7 and 8. Right. Let's write the cycle decomposition of mu. We have 1 sent to 3, 3 sent to 6, and 6 sent to 1. So we close it over here. Go to 2. 2 is fixed, 4 is fixed, 5 fixed, 7 fixed, 8 fixed. So the cycle decomposition of mu is simply this. So if I do not give you this set and simply this cycle, that is an element in, that is an element in S8, we understand 1 is mapped to 3 or sent to 3, 3 is sent to 6, 6 is sent to 1. Because it's an element in S8, we are actually permuting integers from 1 to 8, numbers from 1 to 8. Every other number that you can't see over here must be fixed. Okay, so what are the orbits of mu? What are the orbits of mu in this case? We definitely have elements in appearing in this cycle to be in one orbit. So 1, 3, 6 will be in one orbit. Any other orbits? Yes, right? For which orbit does 4 belong to? Or maybe 2?
The identity.
No, the identity is simply a permutation, right? We are looking at the partition of A by mu. by simply considering its orbits, right? So like I told you earlier, once you have the cycle decomposition, taking into all these disjoint cycles, right? Taking into account all these disjoint cycles, we can build the corresponding orbits. And every element in A is the set containing integers from 1 to 8. Uh, every element in A must belong to at least one orbit, right? Must belong to one orbit. 1, 3, 6 will belong in one orbit. Where does 2 go to?
Other singleton sets.
Yeah, it
2.
goes to the singleton set containing 2. Why is that? If you calculate mu of 2 is simply equal to itself. Then mu squared of 2, once again itself. So in that orbit, so we have to find powers of mu of 2. And once you calculate the powers of mu of 2, you only get the element 2. So in that orbit, you only have the element 2. All these fixed elements, if you have any fixed element, right, those will belong in the singleton set containing that element. So we have singleton set 2, then 4, then we've got 5, 7, and 8. These are the orbits of mu. Uh, and how many do we have? 1, 2, 3, 4, 5, 6. Only one containing 3 elements, everything else singletons. And as you can see, those are disjoint. The union gives you A. Okay. Is it clear?
Okay.
Right.
Yes, ma'am.
Right. Now then we have a theorem. Every permutation sigma of a finite set is a product of disjoint cycles. Every permutation sigma of a finite set is a product of disjoint cycles. We have seen this in the previous example here. Sigma can be written as a product of cycles which are disjoint. They have no element in common. Even mu, it is represented simply by one cycle, right? And because it's in S8, we understand that every other element that does not appear over here must be fixed. Okay. Right. Now with this, we are going to define even and odd permutations. So first let me write even and odd permutations, right? Okay. Well, in order to do this, first we define a transposition. A cycle of length 2 is what we define as a transposition, right? So in this, let me write it first. A cycle of length 2 is a transposition, right? So in this case, we understand it's a cycle of length 2. In the cycle, we only have 2 elements. Everything else must be fixed in that case, right? So that is, or I will simply write a transposition leaves all elements but 2, which actually appears in that 2 cycle, fixed, right? For example, if you take this cycle 2, 3, we take it as an element in, let's say, S6. So this permutation is a permutation in the permutation group S sub 6. S6 contains all permutations of elements from numbers from 1 to 6. This is a transposition by the length of this cycle is 2. You only see 2 elements in there. What about the rest of the elements? In a transposition, you have 2 elements that are mapped to each other, right? Everything else should be fixed. So because it's an element in S6, this simply tells you 2 is mapped to 3, 3 is mapped to 2, 1 will be fixed, 4 will be fixed, 5, 6, they're all fixed. This is what I have written over here within brackets, right? Now, we can see, I will ask you to do the calculations, right? We can see that any cycle, say, of length n, if we can write it in terms of the elements A1, A2, A3, let's say up to AN. This cycle, we can break into a product of transposition. So we can write it as A1, AN, A1 and AN. 1, 2 cycle times A1, the one before AN appearing in this cycle. So AN minus 1. And we continue this product of transpositions until we get to the last two terms, which is A1, A3 and A1, A2, right? So any cycle of length n can be written as a product of transpositions. So that any cycle of length n can be written as a product of transpositions, right? So we can write them as product of transpositions. Now this you can actually do by considering these two and everything, right? You can, the calculations, of course, you can go on your own and see. Okay, for example, we can write 1, 3, 6, right? Simply as 1, 6, 1, 3. First element and the last element, and you come and then you take the first element, 1 before the last. Likewise, you continue until you get to the first two consecutive elements or numbers, right? So you can write it as this product, this cycle as the product of these two transpositions, right? Now, we will give this as a corollary. Any permutation of a finite set of at least two elements is a product of transpositions. Right. Any permutation of a finite set with at least two elements is a product of transpositions. How do we take this product? Using this rule over here, using this equation over here. Let's write another, so let's do one more example. Let's consider this. Let's take 1, 6 and 2, 5, 3 in S6. right? In this case, you see that 4 is fixed, 1 is sent to 6, 6 back to 1, 2 to 5, 5 to 3, and 3 back to 2, 4 is fixed. This you can write as a product of transpositions. First one is a transposition, so we don't do anything, we leave it be. 1, 6 will be just that. The second one, however, is a cycle. If you consider this simple one, it's a cycle of length 3. So we are going to break it into a product of 2 cycles. If it's a cycle of length 3, we are only able to break it into a product of 2 cycles, 2 transpositions. Let me put it that way. So we've got first element 2, the last one 3, then 2, 5. Okay.
Okay, madam.
Right. Now, even the identity for any permutation group Sn, when n is actually at least 2 elements, this is the identity permutation even we can write as a product of transpositions. So I'll write it as a remark. Now, remember when I say the product, what you have between these two is the composition, okay? These two is the composition, right? Not between these two. And then we have even over here between these two, they have one element in common, right? It's the composition. You can compose those two and find a cycle in this decomposition where each cycle will simply be disjoint from each other in the decomposition, right? So as a remark, I'll write first of all in Sn for n greater than or equal to 2. The identity permutation 1, usually denoted by 1 in Sn, can be written as the product one, two, 1, 2. That means this identity is equal to 1, 2, 1, 2. Why is that? And it's a product of transpositions, right? Why is that? What is the now 1, 2? If the permutation group has at least 2 elements, we definitely have the permutation 1, 2. That means sending 1 to 2 and 2 back to 1, right? If you have at least 2 elements in the set. So you can permute those 2 elements and get the permutation that is given by this cycle. If I cover this one, just simply this 1, 2, right? And I say that the identity can be written as a product of these two. Why is that? What is the inverse of the permutation 1, 2 given by the cycle decomposition 1, 2?
Is 1, 2, madam.
It is 1, 2, right? How do we get the inverse? We simply start writing. We have done this in a previous lesson. Start with the last element and continue in this direction. Write them down, right? This is the inverse. Now, permuting these two, we see that it's the same element 1, 2. It's the same permutation 1, 2. Start from this last element and list down all the elements until you get to the first one, right? So inverse of 1, 2 is 1, 2 itself. By definition, right, of an inverse, when you take the element composite by its inverse, you get the identity permutation, right? So even the identity, when you have at least 2 elements in a permutation group, you can write as a product of transpositions as given over here. Now, um, the representation of a permutation may not be disjoint, right? E is actually not disjoint in most cases, right? And definitely E is not unique. Why is that? When we take this product of transpositions into account, that is, okay? Because we understand every permutation can be written as a product of transpositions. Because of that, we now see this the representation given by this transpositions may not be disjoint, In some cases, it could be, and definitely is not unique, right? So let me write it. The representation Sn may not be disjoint, and it is not unique, right? And this representation is not unique. Why do I say this? May not be disjoint. Some permutations you can simply will simply be two cycles, right? For example, 2, 3 in S6. Now this is a disjoint because there is only one cycle. There is no other cycle to compare. So there's that. And if you take mu to be 2, 5, 3 of S6, right? You can write this as the product of transpositions 2, 3, 2, 5. Now this is not disjoint because you have this element 2 in each cycle. So the representation, it's not disjoint, these transpositions, right? Why is it not unique? For any representation will never be unique. Why? If you go to this one, sigma 2, 3, this is the same as writing 1, 2, 1, 2, 2, 3. Because the product of these two will give you the identity. So identity times 2, 3 gives you the permutation back. So you see, you can get different representations for the same element. You can even add a pair of these two transpositions at the back, even still get the same element, right? So the representation is not unique because of that. Okay. Right. Now this theorem is important. With this, we move on to even permutations, odd permutations. With that, we move on to the alternating group. We will define the alternating group A. No permutation in Sn can be expressed both as a product of an even number of transpositions and as a product of an odd number of transpositions. Now, take any permutation in Sn, right? You can express it using a product of transpositions. It's either going to be an even number of transpositions or an odd number of transpositions, never both. It can't be in one representation. It's not going to be like this. In one representation, you have an even number of transpositions. In the other, an odd number of transpositions. No, it's never like this. For example, you see, even if you want to take a different representation for this one, you start off with this transposition, right? It's given as a 2 cycle, which is a transposition. So it's given as a product of transpositions already. Simply one transposition. So how many transpositions are there? One, an odd number. To change this representation, how many did we have to add to the product? Two, because the product of these two only will yield the identity. So for one, we add two. Once again, you have an odd number of transpositions. If you want to change this representation, you have to keep on adding two transpositions at a time. So you will stay as an odd number of transpositions in that case. Even over here now, mu is given by this product. You have two transpositions, an even number. If you want to take a different representation of mu, what do? We multiply by the identity. And identity can be written as a product of two transpositions. Once again, we keep on adding two to take different representations of the same permutation. Because you add two, if it's an even number of transpositions, with this addition, you will end up with another even number of transpositions, never an odd number. If it was an odd number of transpositions to begin with, once you add two, you end up with another odd number of transpositions. Okay, right. Okay, so example. Okay, no, before this, we write this definition. A permutation of a finite set is even or odd, right? Even or odd if it can be expressed as a product of even number of transpositions. If it we say that it's odd if it can be expressed as an odd number, a product of an odd number of transpositions, even or odd number of even number of transpositions. So coming back to these two examples, in this case, mu is given as the product of two transpositions. 2 is an even number, therefore mu is even. The permutation is even. If you look at sigma, it's simply written as the one transposition. 1 is an odd number, therefore sigma is odd. Mu is even, sigma is odd, right? Now, the identity permutation is defined to be an even permutation, even for n equals 1. The identity permutation, I mean, if you come over here, for a set with at least two elements, the identity can be given as the product of these two. Because we see two transpositions over here, we can easily see that the identity is an even transposition. What if we are simply talking about S1, right? In this case, we are simply considering permutations of a one element set. So it will definitely be fixed. There is only one set, one element. It will be sent to itself. So the identity permutation is the only permutation uh, in this permutation group. So you definitely can't write it as a product of two transpositions. But in this special case, we define this identity permutation to be even, right? If n equals 1, this is the case, right? We define, in this case, one to be even because there is in this case, there is no transposition 1, 2 in this case at all. It's only containing one permutation, which is the identity permutation, fixing that one element, right? Okay. If you take 1, 4, 5, 6. This cycle, if we write it as a product of transpositions, we can write it as 1, 6, first element, the last one, times 1, 5, and then 1, 4. How many transpositions are there? 3 transpositions. 3 is an odd number, so this is an odd permutation. This is an odd permutation. Okay. Right. With this, we will we will discuss the topic of the alternating group AN. Denoted by A sub n. Right? Okay. Now, this alternating group AN is actually a subgroup of Sn, the permutation group over n elements. And not only that, it's actually a normal subgroup. So before we define this, I will make a claim that for n greater than or equal to 2, because when n is equal to 1, the permutation group S1 simply contains that identity permutation. That's it, right? The number of even permutations is even permutations in Sn is the same as the number of odd permutations in Sn. Right. We will prove this claim. We will prove this claim. Before that, let's denote by AN the set of even permutations in Sn. And by Bn, we denote the set of odd permutations. Denote the set of odd permutations, right? Now, let's look at one example to try and understand this. Let's take S3, which we are very much familiar with. And what are the permutations? What are the elements in this group? You've got the identity, then 1, 2. Then we have 1, 3, 2, 3, 1, 2, 3, and then 1, 3, 2, 1, 2, 3, 4, 5, 6. All 6 elements are there. Okay. So what goes inside AN? What are the even permutations in S3? So instead of writing AN, I will write A3. Even permutations of S3. Identity is in there. Identity will be even always. It's an even permutation. Even for n equals 1. What else is there? And then B3 represents the odd permutations. Then we have this permutation 1, 2. Is it an even permutation?
Yes, madam.
How is that an even permutation? How many transpositions are there in this permutation? Only one transposition, only one 2 cycle, not the number of elements inside. It's not about the number of elements inside. It's about the number of transpositions in the product of this permutation, or the number of 2 cycles in the product, right? I shouldn't say number of 2 cycles. Any permutation you can write as a product of transpositions, and in that representation, you have to find the number of transpositions. If that number is odd, the permutation itself is odd. If the number is even, then the permutation itself is even. Now, in this permutation, it's already a transposition. It's a 2 cycle. So how many transpositions are there? Just one. Therefore, that's an odd permutation. So 1, 2 is an odd permutation. If you go to the permutation 1, 3, it's already given in the representation as a 2 cycle. So once again, 1, 3. Then what else? 2, 3. What about 1, 2, 3? If you take this element 1, 2, 3, you can write it as a product of transpositions using that rule that we saw earlier. You can write it as 1, 3, 1, 2. So this is given as a product of transpositions. How many transpositions are there in this product? 2.
2.
So the permutation itself is even. Right? So 1, 2, 3 belongs in here. 1, 3, 2 also will go in here. Is it clear now?
Yes, madam.
Now in A3, you have how many elements? 1, 2, 3. B3 also you have the same number of elements. Not only that, A3 is disjoint from B3. Why is that? You don't have a permutation which is both odd and even. It's either even or odd, right? So they don't have common elements. Not only that, when you union these two up, you see you get S3. Right? So with this, we understand, we see several things. And even from the definition, this is simply given. AN union BN simply gives you SN. AN is disjoint from BN clearly, right? And the claim, which we have to prove, says that AN and BN have the same number of elements. Now let's go to prove this claim. To prove the claim, what we are going to do is, now to prove the claim, and the claim is the number of elements in AN, order of the set of AN, and the number of elements in BN, order of BN, they are the same. This is the claim. This is what we have to prove. What we are going to do is, we will define a function from AN to BN, which is 1 to 1 and onto. 1 to 1 and onto. If it is 1 to 1 and onto and Sn is a finite set, then this must have the same number of elements as this. Okay? Now to prove the claim, we will define a one-to-one, and onto function from an to bn. From an to bn. Right. Okay. Now, let's take, in this case, observe that n is greater than or equal to 2, right? So we already know in Sn we have the element or the permutation 1, 2. Let me write it in. We have the cycle or the permutation 1, 2 in Sn. It's definitely in there. For S2, this element is in there. That's the only element different from the identity. S3, even for any higher n, this will definitely be there, right? So let's take 1, 2 to be 2. Let's denote it by 2. By 2, let's denote 1, 2. Right? Now, define, like I told you, we are going to define a map between an and bn, and we will show that this is a one-to-one and onto function or a bijective function. Define lambda tau from an to bn by lambda tau of sigma, where sigma is an even permutation, and this will be mapped to 1, 2 of or I will say 1, 2 of sigma, or I actually want to use the term tau of sigma. Lambda sub tau of sigma will be mapped to tau sigma. Right, now observe that this is a well-defined function. Well-defined one-to-one and well-definedness we will prove using an if and only if statement. But observe that taking an even permutation. This is an even permutation because it's taken from an. What does it mean? When you take its representation by a product of transpositions, you have an even number of transpositions. You take that and you map it to tau times sigma. Tau is a transposition, which is this fixed transposition 1, 2, right? So now this is also a permutation in Sn. Not only that, it's an odd permutation. Why? In sigma, we already have an even number of transpositions. And to this product, you take another transposition. So you have an even number of transpositions plus 1 will give you an odd number of transpositions. So in this product, you see, we end up with an odd number of transpositions, obviously an element in Bn, right? Okay. Now, let me write it. We'll observe that for an even permutation, sigma in An, we have tau sigma, which is simply 1 to sigma, to be an odd permutation. Right? Okay. Now to prove that this sigma is, this lambda of tau is 1 to 1 and is also well defined, let's take any even arbitrary even permutations from an as sigma and mu. Now take sigma mu from an, right? Then lambda tau of sigma is equal to lambda tau of mu if and only if, by definition of lambda tau of sigma, we have tau of sigma equals tau of mu. This is if and only if tau is equal to mu. Why is that? Why do we have this? This is because this is a permutation. Tau, which is given by the transposition 1, 2, is a permutation in Sn, right? So it's an element in that group. The inverse for that exists, and the inverse is unique. We take the inverse on both sides of tau in order to get to this other step. In this case, by after taking inverse of tau on the left on both sides, we see that we end up with sigma equals mu. So because inverse of tau, which is simply 1, 2 itself, exists and is unique, right? Therefore, going in the forward direction, we see that it's a one-to-one function. Going in this other direction, starting from here and coming back to here, we see that this is, sorry, a well-defined function. Therefore, lambda tau is well-defined as well as one-to-one, right? It's well-defined as well as one-to-one. Now we have to show that lambda tau is an onto function. So we take any element from Bn. That would be an odd permutation, right? So let rho be an element in Bn. Then observe that tau inverse rho is given by 1, 2 rho. Why is this? Because tau is given by 1, 2, and we know tau inverse, which is the inverse of 1, 2, is simply 1, 2, as we have seen earlier today also, right? Now, tau inverse of rho is an element in an. Why is that? Rho is an odd permutation. That means once you express it as a product of transpositions, you have an odd number of transpositions in there. And if you take its product by 1, 2, just one additional, so you are adding one more transposition to this product. So you have an odd number plus one more, which is an even number of transpositions in the product. So we understand in this element, you have an even number of transpositions in the product so that it actually belongs to an. Right? Now you see, for any row that you take from Bn, tau inverse row ends up in An. Not only that, when you take lambda tau of this element, this by definition of lambda tau times tau inverse of rho, we simply use the fact that this all these elements are elements in a group, and binary operation composition is associative. So we've got tau times its inverse is simply the identity. Identity times rho is simply rho. So this element is mapped to rho, which is an arbitrarily chosen element in Bn. Therefore, we see that lambda tau is onto as well. so that we have the order of an to equal the order of bn, right? So that we have the order of an to be equal order of bn. Now observe how many elements do we have in an. This is easy to calculate. Observe that Sn has n factorial elements. And we know that we previously observed that An is disjoint from Bn and their union gives you Sn. Now from this theorem, we see that they have the same order, right? So this simply means you have An and its complement must be Bn. Anyway, by definition of those two, we see that the complement of An is Bn. Not only that, order of An plus, because of this one and this, order of An plus order of Bn must equal the order of Sn, and those two are the same. So order of An and Bn must equal 1/2 of the order of Sn. So factorial n over 2 it must be. Okay, right. Okay, with this we'll go to a definition. The subgroup of Sn, now we are going to define the alternating group, which is this An that we have seen so far, right? The subgroup of Sn consisting of all the even permutations is even permutations An is what we call the, let me write, alternating on n letters, right? So this An is what we call the alternating group. If you go to the previous example that we did, we have seen that this is actually a subgroup of S3. We have seen this in a previous example. This A3 that is given over here, it has the identity 1, 2, 3, and its inverse is 1, 3, 2. We have seen that A3 is a subgroup of S3. Not only that, this is a normal subgroup as well. Why is that? Let me first write An is a subgroup of Sn, right? And if you go back to this theorem that we did last time, let G be a group, H a subgroup of G. If the number of left cosets of H in G, distinct left cosets of H in G is 2, if there are only 2 left cosets of H in G, then H must be normal in G. So now, what we are going to do is see the number of left cosets of An in Sn. We understand that the number of left cosets of An in Sn must be 2. Why is that? Once again, if you go back to this one, we know that An is a subgroup of Sn. So An by itself is a left coset of An in Sn. This is one left coset, right? If there is another distinct left coset of An in Sn, it must have the same number of elements as An, right? So what is the other set having the same number of elements as An over here? It's simply B, and it's not just because of that. because there are some other properties that we have learned for left cosets. Let me list them all down. First, let's write distinct cosets of an in Sn are an and Bn. This is because an intersection Bn is disjoint. There is no intersection. And the number of elements in An is the same as number of elements in Bn. Not only this one, An union Bn is equal to Sn, right? If you recall the properties of cosets, we understand any two, for a given subgroup of a group, in this case, An is the subgroup of Sn, you take any coset of An in Sn, any two cosets, they could either be identical or disjoint. First thing is that, identical or disjoint, right? We always know An is one coset. The subgroup itself is a coset, right? Not only that, all cosets, if we have actually proved this one, all cosets have the same number of elements, right? So together with all these details, we see that An has only two distinct cosets. Whenever you pick an element in An and find the coset with respect to that, you get An. And any other element that is from the complement of An must belong to a coset that is disjoint from An. That is disjoint from An. And it could only be its complement because the complement, its disjoint, have the same number of elements as An. Not only that, the union of those two gives you Sn, sorry. Right? Therefore, we understand the number of elements of An in Sn is equal to the number of, not number of elements, number of left cosets of An in Sn is equal to 2. Therefore, recalling the theorem that we did last time, we must have An to be a normal subgroup of Sn. And this holds only when n is greater than or equal to 2. When n is equal to 1, then S1 is simply equal to A1 because the identity element is an even permutation, right? Identity element is an even permutation, and therefore it's contained in A1. So A1 is a subset of, A1 is essentially S1. It's the same as S1. And we know for any group, the group itself and the trivial group will always be a normal subgroup of itself. In that case also, An is a subgroup, normal subgroup of A1 is a normal subgroup of S1. Right? Okay. Right. So we understand this alternating group is a normal subgroup in Sn. Okay, now we are going back to normal subgroups. Now we are going to define the quotient group. Do we have any questions so far?
No, madam.
Right. Okay. This is sometimes called the factor group. We will go by the name quotient. Okay, now what do? We take G to be a group. Let G be a group and N be a normal subgroup in G, right? Then by the quotient G over N, now this is, we are going to define this to be a group. In order to do that, we have to define a binary operation over it, and we have to see what sort of elements it contains, right? By G over N, let's denote the set of all left cosets of N in G. That means by G over N, the quotient by N of G, we define all these left cosets, right? And recall that Gn is defined to be the set containing elements of the form G times simple n, where these simple n's come from n, right? So now this set is defined to be the set of all left cosets of n in G. Observe that in this, n is a normal subgroup of G, right? Now we are going to define a binary operation on this set, which I will indicate by star for now. Define a binary operation star on G over N by taking two elements G1N star G2N to give you G1, G2N. Right? If I further clarify this, what we mean by all this, let's suppose our group G is under the binary operation. Oh, if you have G to be under the binary operation given by this circle, then by G1N star G2N, we mean G1 circle G2N. So once you apply this binary operation, we get G1 circle G2. For G1, G2 taken from the group G, G1 circle G2 means an element in G once you apply the binary operation over G. What do we have in this? This is an element in this set. Why? G1 circle G2 is an element in G. This is the left coset of N by the element G1, G2. So obviously what you get on this side is an element in this set. But we have to see that this binary operation is well defined. It's a proper binary operation defined on this set. How do we do this? Um, let me write first. Let's prove that star given over here is a binary operation on G over N, right? To do this, suppose G1N is equal to H1N and G2N is equal to H2N. Why have I taken these two equations over here, equalities over here? What is given over here? We have G1N, the left coset of N by the element G1. And it's equal to H1 times N. What does it mean really? That means the same coset, right? The same coset taken by a different element H1. H1 different from G1. For example, if you take N, right? In this case, yeah, let's go over here with Gn. If you take this G to be the identity element, now the identity element is already in N. What do we get in this set? We get, once again, N. Because you have, instead of G, the identity over here. Identity times n will simply end up being n, and you are taking all elements that are in n. So identity times n is simply equal to n. On the other hand, I will take another element from the normal subgroup n that is different from the identity, right? What do we get in this case? What do we get? I'll just within brackets, I'll write because now we are writing inside the proof. For the identity and n in n, we see that identity times this n, the left coset of n by the identity is simply equal to n. Not only that, by this element n, if you take the left coset of this simple n, which is also an element in n, it also ends up being n, right? So we understand En is equal to n1. This is equal to n1n, where n1 is another element in the normal subgroup n. So the same coset you can write with different representatives in that coset by taking different representatives, right? So what are we going to prove over here? We are going to say that even though you take different representatives and different representations for the same coset, once you apply the binary operation, you should get the same thing, right? You should get the same thing if this is a real binary operation, right? So we are taking two different representations. In other words, we are writing the same coset using different representatives. We need to show G1n star G2n is equal to H1n star H2n. When you take G1n star G2n, it should be the same as H1n star H2n, because once again, G1n and H1n are the same coset taken by different representatives, right? In other words, we need to show that G1n star G2n is simple G1 G2n. We want to show that this is equal to H1 H2n, right? Okay. Now we have G1 to be an element in G1n. Why is that? Because the identity is in n, right? And if you go back to this set, Gn contains elements of the form G times simple n, where this comes from that normal subgroup. Because it's a normal subgroup, the identity is in there. So whatever representative that you put over here must belong in this left coset, right? When you take the product by the identity. Right, so we see that G1 must belong in this set because the identity is in N. And so G times the identity equals G is in N, right? And then similarly, G2 is also in G2N because G2, this is G1. G2 times the identity, which is an element in N, and it's equal to G2, must be in N. Must be not in N, sorry. G2N must be in G1N. Not in N, the left coset, okay? Not necessarily in N. Okay. Now, because G1 is in G1H, we have G1 to belong in G1N, which is equal to H1N. This implies now G1 is an element in H1N as well. So we are taking this representative and we will write G1 as H1 times N1. And because G2 is an element in G2 and this left coset, which is equal to H2N, we can write G2 as H2N2 for N1, N2 elements in the normal subgroup N. Right? Therefore, we see that G1, G2, this product, is now equal to H1N1, H2N2. Now, let's go to G1, G2 times N, this left coset of N by the element G1, G2. This is equal to H1N1, H2N2, N. This is equal to, by applying by seeing this H1N1, H2, N2N, right? This is equal to H1, N2, H2N. Why is that? N2 is an element in N. So when you take the left coset by an element inside the set, right, inside this subgroup, it gives you the subgroup. We have seen these properties when we discussed left cosets or cosets in general, right? So we write because N2 is an element in N. This is equal to H1N2 NH2. Why is that? Because N is a normal subgroup in G. When N is a normal subgroup in G, the left coset is equal to its corresponding right coset. So H2N must equal NH2. These also we have seen before. Once again, now we have N2 times NH2. This is simply equal to N. Why is that? Because N2, this is N1 over here, sorry. N1 over here is an element in N, right? Now, once again, what we do is, instead of NH2, we will take H2N. This is also once again due to N being a normal subgroup in G, right? So exactly what we wanted to show, G1, G2N is equal to H1, H2N. We are done. Star is a binary operation. No matter which representative we take, no matter how you represent the left coset, when you apply this binary operation, you get the same answer for these two cosets. Sorry. Okay. Now we will show that G over N by this star is a group. We already know that star is a binary operation defined on the quotient G over N, right? This is what we call the quotient group, right? So we had to prove that this is a group. All together, quotient group. First, we have to prove associativity. To prove associativity, we take any three elements from this set. Let's take them to be G1N, G2N, G3N taken from G over N, the quotient. We have G1N star G2N. Then we apply the binary operation to G3N. This, by definition of star, is equal to G1N star G2N. I was supposed to apply the binary operation for this one. This is equal to applying the binary operation over here. We have what? G1, G2, N star G3N. Once again, applying the binary operation, we see that this is equal to G1, G2, G3, N. Now, G1, G2, G3, they are all elements in the group G, right? And this product is by the binary operation over G. And that is associative. So using that associative property, we see that this ends up being G1. We can write this as G1 times G2, G3. Now, once again, applying star, using the definition of star, we see that this is equal to G1 n star, G2, G3, n. Applying star over here, definition of star over here, we see that this is G1 n star, G2 n star, G3 n. So associativity holds. Now we have to show that there exists a unique identity element for this group. The identity is actually given by n, which is the normal subgroup itself. Identity is n, which is equal to the identity times n, right? Let's take, to see that it satisfies the condition of it being an identity, let's take any element Gn from the quotient, the set G over n, then n times Gn, n I will simply write as En star Gn. By definition of star is Egn. This is equal to, E is the identity over G, in G. Eg simply gives you Gn. This, so apply, take the binary operation or take star for these two elements, you end up with Gn. Now this I can write as Ge times n. Going back to the definition of star, we see that this is Gn star En. So it satisfies the condition for it to be an identity. This is the identity element. Okay. Now let's take any element in this set and we have to find its unique identity. Let Gn be an element in this quotient. The inverse of Gn is given by G inverse of n. Why is that? When you take star over these two, we see that by definition of star, it ends up being G inverse n. G inverse is simply the identity times n, which is the identity for this group. This is equal to G inverse G times n. Once again, using by definition of star, we've got this to be G inverse n star Gn. And the identity is unique. Why is that? G inverse is the unique, sorry, not the identity. The inverse is unique because G inverse is the unique inverse of G. Therefore, we see that the inverse of Gn is simply G inverse n. Right? Therefore, all axioms are satisfied. We see that this by star is a group. It is a group. Okay. Right. So notation from here on out, when we understand what the underlying binary operations are for the given groups, let's simply write. We will simply write G1n times G2n instead of G1n star G2n. Instead of writing star, we will simply write it as a product. So we understand it's the binary operation of the quotient group that we are talking about when we are presented with this product. Okay. Do we have any questions so far?
No, madam.
Shall we take a look at some examples then?
Okay.
Okay, let's start with the group Z6. Right? This is the group containing integers from 0 to 5 under the binary operation addition modulo 6. Right? And let's take its subgroup n containing 0 and 3, which is a subgroup of Z6. Observe that n is a normal subgroup in this. Why is that? Why is it a normal subgroup? Because Z6 is abelian. In an abelian group, any subgroup will always be normal, right? Z6 is abelian, right? Now let's find the quotient group and calculate or write down its multiplication table, right? Okay, so we see that Z6 over n is simply given by, we have n, then we have 1 times n, then we have 2 times n. Right, how do we get this group? We are supposed to find all left cosets of n in Z6, right? So we start off with 0. 0 times n would simply mean you don't really have to write those two because it's the identity element. When you take the left coset of a given subgroup by the identity, you get that subgroup itself, right? So we have definitely one left coset to be n 0, 3. Now let's find the other coset by an element that does not appear over here because cosets are always, any two left cosets are either always disjoint or identical. So let's take an element that is not in there. Let's go with 1. 1n by definition is what? 1, the binary operation over Z6 is addition modulo 6, simple n, where the simple n comes from our normal subgroup n. What sort of elements does it contain? But when you take n to be 0, 1 plus 0 is 1, 3 plus 1 is 4. So it contains 1 and 4. Then we have 2n, 2 addition modulo n, where n comes from the normal subgroup n. We add 2 to each of these elements. 2 plus 0 is 2, 2 plus 3 is 5. As you can see, all elements in Z6 are here. There is no other element that does not appear in any one of these. Mutually disjoint these three have the same number of elements. These are all the distinct left cosets of n in Z6. So this set contains these elements, right? Okay, now let's find the multiplicative group. I'll just indicate the binary operation over here by star. We have n, 1n, 2n, n, 1n, 2n. N star n. How do we find it? Now, n is the identity, so we don't have to spend time really finding those elements. N star n would simply give n. 1n star n would simply give 1n. This is because n is the identity, as we have seen from the previous proof. This is 2n. If you go along this row, we once again get all these elements. Get to this element, 1n star 1n. If you calculate it separately, we have 1n, 1n. This is the element that comes over here. This is equal to what? 1 addition modulo 6, 1 times n. 1 plus 1 divide by 6, take the remainder. 1 plus 1 is 2, divide by 6, take the remainder, you get 2n. So this over here is 2n. To find this element, we have 1n times 2n. This is equal to what? 1 addition modulo 6, 2n. 1 plus 2 is 3. Divide by 6, take the remainder. You have 3n. But now we don't see any 3n over here. What does this equal? What does this?
N.
It's equal to n. Yes, because 3 is an element inside n. So this is equal to n. This over here becomes n. Once again, 2n plus 1n also the same. N. To find this element, you have 2n times 2n. We've got 2 addition modulo 6 to n. 2 plus 2 is 4. Divide by 6, take the remainder. We've got 4n. Once again, we don't see any 4n over here. What does this equal?
1N.
1n, right? Because 4 is an element in the coset 1n. So 4 is another representative for this same coset. So it's 1n. This is the multiplication table, right? You can easily see that it's a group. By just looking at this, you can identify the inverses as well, right? Inverse of 1n is what? We go along this, you can either pick, sorry?
2N.
2n, because 2n times 1n gives you n, which is the identity. So along the identity of n is itself, identity of 1n, because you see n over here, it's 2n. For 2n, it must be 1n, once again, because 1n is the inverse of 2n, right? As you can see, we see the identity over here. Right. And now observe that this group has 3 elements. Not only that, this is structurally actually similar to Z3 as well. If I take the group Z3 over here, simply for you to better understand and see it, to compare the Z3, it's got the element 0, 1, 2, right? And then the binary operation would be addition modulo 3. So addition modulo 3, we have elements 1, 0, 1, 2, 0, 1, 2. If you apply the binary operation, we have 0, 1, 2, sorry, 0, 1, 2, 1 plus 1, 2, divide by 3, take the remainder, it ends up being 2. 2 plus 1 is 3, so 0. 2 plus 1 is 3, 0. 2 plus 2 is 4, so 1. If you compare these two, they're essentially the same, even though they have two different, obviously, elements, structure-wise, the same. There is a correspondence between n and 0 over here, 1n and 1, 2n and 2. Inverse of 1n is 2n, inverse of 1 is 2. Inverse of 2n is n, inverse of 2 is 1. Likewise, structurally, they are the same, right? So let me write it over here. So in other words, those two groups are isomorphic, right? You can see, you can actually write the isomorphism by mapping n to 0, 1n to 1, and 2n to 2. Okay, so let me write this. The group Z6 over n is structurally similar to Z3. In other words, Z6 over n is isomorphic to Z3. You can even show this by giving a proper isomorphism. Okay, right. Now let's do another example. And before we actually move on to another example, check this one out. Take 1n or even 2n, even 2n works in this case, for this particular group. Take 1n. 1n to the power of 0 simply gives you the identity, right? And then 1n to the power of 1 gives you 1n. 1n squared. That means 1n, 1n. 1n, 1n gives you 2n. This gives you 2n. 1n cubed. That means 1n times 1n, which is 2n. 2n times 1n, which is once again n. So we see that by 1n, we have generated all elements in the group. Not only that, it is of finite order. Order is 1n cube is simply n. This tells you order of 1n is 3. The entire quotient group given over here is generated by this single element 1n. It is not only generated by 1n, but also by 2n. So we see that this quotient group is cyclic as well. Now see the correspondence. This is abelian. This is a symmetric matrix you see over here. Therefore, this is abelian. Right? This quotient group is abelian. Z6 is also an abelian group. Not only that, Z6 is cyclic. You can generate it by 1. And corresponding to 1, we have 1n, which also generates this given quotient group. Right? So from this, we see that this quotient is generated by 1n. It's a cyclic group. Right? Okay, let's take a look at one more example. Consider the additive group of integers. And let's take n to be 4 times z. We know that this is a subgroup of z. Any subgroup of all the groups of the form m times z is a subgroup of z. This we have seen before, and this contains all multiples of 4. So we have 0, plus or minus 4, plus or minus 8, likewise, all these elements, right? Now we see that n is a normal subgroup of z. Why is that? Once again, this is because Z is abelian. If it is an abelian group, any subgroup of it will always be known. Right? Z is abelian. Now, let's find the quotient g of n, which is simply z. Here g is the set of integers, the group of integers, 4z. This is given by what? N and 1 plus n, 2 plus n, and then 3 plus n. 4 plus n is back at 10. These are the distinct left cosets of 4z in z. If you definitely 4z by itself, 4 times z, is a left coset in this group, right? Left coset of itself in the group. Then we take integer 1. Right? And we have done this example even in a previous class. Can list them down. We have 1, then we have 1 plus 4z. Simply contains integers of the form 1 plus m, where m comes from 4 times z. So it contains all integers. When you add to any of this, 1. We've got to negative 4, we add negative 3. Negative 3, 0, 1, then 5. Then we have 9, likewise, right? Then we have 2 plus 4z. This is the other coset. To all these integers, we add 2. So we have negative 2, 2, 6, likewise. Then we have 3 plus 4z. To all these integers, we add 3. We've got -1, 3, 7, likewise. Now, if we go to 4 plus 4z, right? Sorry. This is equal to all of these integers, we add 4. -4 plus 4 is 0. So we have 4, 8. What do we get? We simply get 4z. So these 4 that are given over here are the only distinct left cosets of 4z in the set of the group of integers, right? So we have the quotient to contain these elements. Now let's find its multiplicative group. We have n, 1 plus n, 2, or you can simply write 2n. I have written plus because we have done this example. We have found these cosets using this notation. This is star over here, and let's put n over here. Two and 3 plus n. Because we are taking by the identity, this will simply be n, 1 plus n, 2 plus n, 3 plus n over here. 1 plus n, 2 plus n, 3 plus n. This element, 1 plus n times 1 plus n. How do we find that element? We simply take 1 plus 1 times n. 1 plus 1 is 2, so it ends up being 2 plus n. Over here, we have 2 plus n times 1 plus n. So this will be 3 plus n. Over here, we have 1 plus n times 3 plus n. That means 1 plus 3 times n. 1 plus 3 is 4. 4 plus n is simply n. So this will be n. And over here, we have 3 plus n. We have n. Here we have once again n, 1 plus n. Here we have 1 plus n because 3 plus 2 is 5. 5 plus n, so it actually is over here. Here 5 is over here. So 1 plus n. And this ends up being 2 plus n. Right? I know this is a little bit like not very tidy, but you understand how it all came to be the group, the multiplication table, right? And if you look at this one, this is actually structurally very similar to Z4. This is structurally very similar to Z4. If I try and separate this, little bit hard the way I have written it, right? Structurally, so essentially, they are the same. In other words, Z over 4Z, the quotient group is isomorphic to Z4. Z4 given by 0, 1, 2, 3. Over here, this n would correspond to 0, which is the identity. 1 plus n would correspond to 1. 2 plus n would correspond to 2. 3 plus n would correspond to 3. Right? So we have Z over 4Z isomorphic to Z4. If I write the elements Z over 4Z, we have elements n, 1 plus n, 2 plus n, 3 plus n. If I denote n by 0 bar, 1 bar, 2 bar, 3 bar, simply taking into account because n is simply 0 plus n, right? Taking into account the representatives, I will represent each of these elements, these cosets by 0 bar, 1 bar, 2 bar, and 3 bar. And in Z4, we have the corresponding elements 0, 1, 2, 3. So it has this one-to-one correspondence. we can easily see that there is an isomorphism mapping these corresponding elements. Mapping 0 in Z4 to the corresponding coset containing this element. Likewise, you can do this, right? So we can easily see that there is an isomorphism between these two groups. Okay. Have any questions so far?
No, madam.
Okay. Right. Now let's do one property of quotient groups. This we have seen, okay, in these examples. Properties of quotient groups. Let's take G to be a group and N to be a normal subgroup in G. Then, if G is abelian, then G over N is also abelian, right? How do we see this? How do we prove this? Let's take any two elements in G over N. Let's take them to be G1N, G2N in this quotient group G over N. We want to show that these two arbitrarily chosen elements, we can commute and still get the same answer. So we have G1N times G2N. By definition of the binary operation defined over the quotient, we write it as G1, G2N. This is equal to G2, G1N. Why is that? This is because G is abelian. And once again, the definition of the binary operation over the quotient group yields G2N times G1N. See, we have commuted these two elements. We are able to commute the two elements because G is abelian, right? Okay.